coming today. Peter gave some background context to why everyone's here. I'm here today to represent Polymer Labs. We're building Polymer, an IBC hub, to bring IBC transport layer to all chains. The title of the talk today is Optimistic About ZK. If you guys are familiar with interoperability, there's a number of approaches to verifying the state of one chain on another. You can do naive verification, you can do optimistic verification, and there's a number of teams working on applying zero-knowledge proofs to verification at the client or state layer as well. But today we're going to talk about how combining both optimistic and ZK verification techniques can get you nice properties and benefits from both. So some personal background on myself. I'm a co-founder at Polymer and also technical lead. I have some previous experience working on distributed systems. I worked on an open source time series database at a small startup that spun out of Uber, and a number of other startups on infrastructure as well. So the agenda today is we want to walk through a journey. We want to take everyone from basics of a blockchain, review blockchain interoperability, talk about optimistic verification, applying zero-knowledge proofs for verification, and ultimately end up at discussing optimistic ZK. I want to say that throughout this presentation, we're going to be straw manning throughout this process, meaning that we're just going to be describing things at a fairly high level. Well, not that high of a level. I know that some of you here are not developers. I apologize. But high enough that we can kind of move at a reasonable pace. So to kick things off, we're going to discuss blockchain consensus. Like, what is a blockchain? What is consensus? So to understand blockchains, we wanted to produce some definitions. So if you think about a blockchain abstractly, it's a global state transition function of which a number of nodes come together and agree on and observe what has happened before and after. Concretely, what this means is there's some number of nodes. They observe a state transition function from one block of a blockchain to the second block. And there are obviously some side effects that happen as a result of this state transition function. So what are some of the side effects? First off, there may be some changes to a local store on the blockchain, and these are the result of perhaps read, write, and delete operations as a result of executing those transactions. Logs and events are also produced throughout the execution, and we can also have validator changes, such as changes in the validator weight in the proof-of-stake algorithm. Perhaps you're using proof-of-stake as a consensus algorithm, or changes in the validator set itself. The results of this are encoded in the form of block headers. So we have a number of blocks. There's some transactions associated with it. The header is a summary of what happened. In the header itself, we may have some state root, which is a commitment or a Merkle commitment to all of the key value pairs in that blockchain. So all of the data. This is consistent across headers, and it changes over time. There may be some transaction hash or root. There may be some validator set hash or root. The transaction hash would change on a per block basis. The validator set may change on a per block basis as we have validator changes. This header is then attested to via public key cryptography. Every single validator node generates a public and private key pair. We're not going to go into how this works because it's outside the scope of this talk. But at a really high level, I have an Alice and Bob example here. So we have Alice, the validator, who has a header. Alice takes that header, serializes it using some format, be it protobuf, JSON, or otherwise, hashes the serialized bytes to get a succinct hash, signs that hash with their private key, and produces a signature. That signature is then shared with Bob, the validator. Bob, the validator, has knowledge of Alice's public key and uses that public key to verify that the signature that Alice shared matches the hash of the header that Bob has received. And this is done at scale over any number of validators. The second part is interoperability between chains. We're going to review the OSI model and how the OSI model maps to the interoperability model within Web3. You have an application layer, a transport layer, and a state layer. For the purposes of this talk, we're only going to discuss the state layer. The state layer is how do you transport or how do you verify the state of one chain on another? This is analogous to physical network links in the Web2 networking model or the OSI networking model. So at the state layer, we have a connection that's established, and this is done generally with a light client of one chain on the other, and the light client of another chain as its counterparty. And how do we verify consensus in a connection? A block header, as we presented earlier, is presented to a client that sits on chain. And this is the header of a chain's counterparty that they're trying to communicate with. This header is then serialized using some serialization format. It's hashed to some bytes. Then the on-chain client algorithm will take the public key of the validator and decrypt the signature provided to it within the header information. Compare that to the bytes that it produced from hashing the header and make sure that these match. If these match, then the client algorithm knows that this validator, identified by its public key, has attested to or voted on this header. We can find this information by looking inside the header itself. Inside the header, we'll have some sort of commitment or hash or root of all the validators that are participating in this network. We get a Merkle proof into this validator set hash, which produces some validator information. This will contain the public key of the validator, and this will also contain things like validator weight, or how much stake weight it has in the proof of stake algorithm. We're going to sum up these weights until we reach supermajority consensus. And this is done until we get to that point over a number of validators. So what are some issues with this naive verification process? If you were to do this in the virtual machine of a chain, let's say Ethereum, perhaps the signature scheme used by Alice and Bob to sign and attest to these headers is not efficient to be run within this VM. The serialization scheme can also be an issue. Perhaps you have to do protobuf encoding or decoding, which can also be expensive as well. And also perhaps the pricing of the hash function as it relates to the VM adds additional cost. The proofs can be large as well, since we're checking that we're producing a proof for every single validator in the validator set hash, meaning that we can have very large proof on the order of the size of the validator set. But we can do better than that. What does optimistic verification look like? For the first part, we can take, let's say, a light client, be it 07 Tendermint, which is the one used in majority of Cosmos chains, and cross-compile that to, let's say, a MIPS program. The MIPS instruction set is the MIPS VM is a fairly simple implementation. There's an existing implementation in Canon. It's not production ready yet. It hasn't been audited, but you can use it and you can play with it. And you can probably choose one of these VMs based on how simple it is to implement the instruction set and how simple its memory layout is. So compiling this light client algorithm to a MIPS program, we can have an off-chain relayer execute this MIPS program and generate an execution trace. In the execution trace, for each instruction of the MIPS program that you compiled, you're going to commit to the memory of the MIPS VM. This is then provided and submitted to the on-chain client in addition to a new header. Now, in the general case, your job would be done. In the happy path, this is a valid header, this execution trace is correct, and after some fraud window, be it, let's say 7 days, this new header is accepted onto that client. But if there is fraud, what we have to do is a fraud prover off-chain engages in what's called a bisection game with the on-chain verifier. At a high level, you're performing binary search over all of the instructions within the MIPS program itself in order to find the faulty instruction. So let's say there is 1 million instructions. You would start perhaps in the middle, execute that instruction off-chain, submit that result on-chain, the on-chain verifier would then re-execute that single instruction, check that the results before and after match in terms of its memory layout, agree or disagree. And depending on whether it agrees or disagrees, you would shift the execution window left or right until you would find the faulty instruction in roughly log-in steps. There are some advantages to using optimistic verification, but there are also some disadvantages. So some of the advantages are you can reduce the cost of the system. In the happy path, you're no longer verifying every single consensus proof. You're also reducing the scope of the execution as well. You're no longer executing the entire program, you're only executing log-in of the instructions in that program. There's some caveats here with the cross-compilation, the number of instructions generated from the original program itself. The issues are you have a long latency period. Perhaps you have a fraud window in which you have to wait 7 days, or perhaps even longer, before a client is willing to safely accept that header. There's also the issue of interactive proofs. So if you're dealing with a virtual machine like Ethereum, there's a fairly high base cost, 21,000 gas to be specific, of executing an Ethereum transaction. So when you engage in this bisection game, you're paying this base cost per round. And also perhaps there's no cross-compilation available natively from the light client of the code that you want to use to the instruction set of the VM. So what's a different path that we can take? We can also use zero-knowledge proofs for verifying the consensus of chains. And how do we do that? This is a diagram of a generic zero-knowledge proof construction system. We can say that on the left side, we would implement in the form of arithmetic circuits some definition of the logic of the light client algorithm. Generally, you're defining a set of constraints that are enforced by the verifier when you generate a proof and submit that on-chain. So what's happening is you're essentially proving that the execution of the light client is correct and that the new header that has been submitted is valid and satisfies the consensus rules of the chain itself. While there are some advantages to this, such as you no longer have the minimum latency bound that you had with optimistic verification, and perhaps the cost of executing this is lower than naive verification, the cost can still be quite high. Even the most succinct zero-knowledge proof systems cost about 300,000 gas to verify on-chain. There's also no maximum latency bound. In a system where you have incentives in place to incentivize the submission of this update, you may have to wait a long period before enough incentives accrue until you can make this submission on-chain. Some other issues are that the signing scheme and the hashing function used in the algorithm may not be snark-friendly. This means that when we convert the program into the set of constraints, the number of constraints generated for the program itself might be orders of magnitude larger. And now you end up with massive off-chain prover that takes perhaps a week to generate a proof. Which leads me to part 4. What if we could combine some properties from optimistic verification with ZK verification and get a whole new system? So how is optimistic ZK verification better? First off, you still get the lower cost of connection maintenance property that you get with optimistic proofs. In the happy path, you don't need to verify anything. And now the minimum latency bound of using optimistic verification alone becomes a maximum latency bound. Meaning that if you want to go faster, you can have someone supply incentives in order to speed up that transaction, which is not possible in a purely optimistic system. The zero-knowledge proof is both used as a fault proof to prove fraud, and it's also used as a consensus proof to prove consensus. Beneath the latency bound, or beneath the fraud window, it's being used as a consensus proof, and after the fraud window, it is being used as a fault proof. With the system, you get a dynamic latency-capable system where you can have very fast transactions for highly incentivized networks, and also very low cost for connections that perhaps don't have as much activity going over them. Lastly, I want to call on the audience and viewers in the future to join us in building the future of IBC. We recently started an initiative to fund open IBC research called Open IBC. There are a lot of interesting research items that will further IBC adoption across chains. Feel free to reach out to Open IBC directly, myself at my Twitter handle, or Polymer Labs. Thank you.